So what you need to know for 7.2 is exactly the same that we needed to know for 7.1, which is all the stuff there on the left. So your reciprocal identities, your unlock it, sorry, hang on. Your reciprocal identities, which are the, that cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. And then that you can rewrite tangent as sine over cosine and cotangent as cosine over sine. Your Pythagorean identities, sine squared plus cosine squared equals 1, tan squared plus 1 equals secant squared, 1 plus cotangent squared equals cosecant squared. Your even odd identities, which is where you want to look for the negative. So if you see a negative on an angle, you want to go to your even odd. Where sine and tangent, if I change the sign on the actual angle, it changes the sign on the trig function because those are odd. And then cosine is even, because even if we change the sign on the trig function, it does, or the angle, it doesn't change the sign on the trig function. And then with these, remember their reciprocal functions have the same. So this would be cosecant of negative x would equal negative cosecant of x. This would be cotangent of negative x would equal negative cotangent of x. And then cosine is like, well, it's the reciprocal function for secant. So secant is the other one that is even and would not change. So if I ask for the sign at, let's just say pi over 4, and then I ask for the sign at negative pi over 4, the positive negative sign is going to change. But if I ask for the cosine at pi over 4, and then I ask for the cosine of negative pi over 4, the sign does not change, it's the same. And then the cofunction identities, which is all of these are complements. Sine goes with cosine, tangent goes with cotangent, and secant goes with cosecant. So because it's a complement, pi over 2 is the same thing as 90 degrees, that's why it's a complement, okay? I would say that the sine at an angle is the same as the cosine of the complement to that angle, or the pi over 2 minus that angle. So remember, you want to look for things like the negative angles, the squareds with another number, squareds there, and here you would look for something like pi over 2 minus an angle. And that should remind you to bring you back to those specific identities, and then you're going to use those to simplify your expression. So when you're verifying, and these are just tips, it doesn't mean it works the same every time, but usually you're going to work with the more complicated side first. So if there's two sides, one is really simple, you're going to go to the other side where it's a little bit more complicated and try to simplify that. Don't forget that you can factor expressions, okay? Sometimes that helps you. Usually, if you have like a tangent on one side and a sine cosine on the other, you're going to write that tangent in terms of sine and cosine, or one of the other reciprocal functions. And then don't forget about your Pythagorean identities. When you see something squared, I would always go to the Pythagorean identities first. It doesn't mean they're always going to be used, but usually if you see something squared, it would be used. All right, so that's it. You already know everything you need to know for this section. Now you just got to figure out how to use it. So these examples will just say verify the trig identity, and it's going to look just like this on your quiz. So your work is your answer on your quiz. Obviously, we know what should happen at the end of these. The left side should equal the right side. Now you got to get the steps in between. So let's start with number 1. What side's more complicated, left side or right side? Left side. So let's start there. Doesn't mean it's always going to work, but let's start there. What do you see there that triggers something from that previous slide? Secant squared x minus 1 is what? Tan squared, right? Because tan squared x plus 1 equals secant squared x. So if the 1 is on the side with the secant, then I can actually replace this whole thing with tangent squared. Okay, left side still doesn't equal the right side yet, so I still got to work. What could I do next? So if I go back that route, I'm just going to keep flip-flopping them back and forth, right? Secant would be 1 over cosine. Yeah. What can I do with tangent? Sine over cosine. So they're squares, right? So it'd be sine squared x over cosine squared x over, and then we said secant is 1 over cosine squared x. Still not to sine squared, but we're making some progress. Now what can I do? What do you do when you have a fraction? Keep, change, flip it. So this becomes times cosine squared x over 1. So this is gone. What can I do with those? Cancel out your cosine squared x, and what's left? Sine squared x. And that was my goal. As soon as I get that left side to equal the right side, I know I'm done. So I cannot stress the importance of making sure you write out each step here enough. Again, I know that what you're supposed to get there as the end result, because it gives it to you. It's basically telling you what that answer is at the end. But you've got to make sure that you can get there with the work, and you've got to show each step. You can't skip steps. Sorry, hang on, let me start in 10 minutes. Okay, move to 2. What's more complicated? Definitely the left. There is nothing you can do with the number 1. So don't even try it when it's by itself. Always start with the other side. What do you see there that you can do? Good, that's a Pythagorean identity. Sine squared x plus cosine squared x would be 1. So I've got 1 over cosine squared x secant squared x equals 1. Now what? I can split this, so it'd be 1 over, like this, 1. Is this what you mean? Yeah. I know it's been a little while, but I told you that you can move things, right? You can move them from the bottom to the top or the top to the bottom, making them their reciprocal function, right? So I can move secant to the top of this fraction by making its reciprocal function, which will be cosine. And now what? Cancel them out. Sometimes there's more than one way to do these things. So if you saw it differently, don't freak out. This one, I don't know how else you would do it, but it happens, okay? It doesn't mean it's wrong. As long as you can get to the end result using correct steps, there can be more than one way to do these. All right, you try 3. See if you could do it. All right, I'm going to challenge somebody from home to speak up. So somebody from home, tell me what's one thing you could change in this.
Change the tan to sine over cosine.
Okay.
And then change the secant to 1 over cosine.
Okay.
Change flip. And then you change flip.
Good.
And then it would cancel.
Perfect. Good job, Brianna. Anybody do it differently? I think that one's kind of the easiest way to do that one. Okay. All right, how about 4? Again, somebody from home, but not Brianna. Ariana, any guesses?
No.
No, I'll give you a hint. Look at the 1 plus cotangent squared. Where's that come from? So Ariana, go back to your Pythagorean identities, right? Do you see one that says 1 plus cotangent squared?
Yeah.
It's close, right? What does it say?
One, it should equal cosecant.
So 1 plus cotangent squared x equals cosecant. Yep. So I can replace that whole thing with cosecant, yes? Ethan Mirabal, how can I rewrite cosecant squared?
1 over sine squared.
Good. Giovanni, what can I do with that?
You can cancel out the signs.
Good. And I get 1 equals 1. Anybody do it differently? No? Anybody from home distribute? So I'll show you that way because sometimes people do that. Distribute the sine squared. I always, if there is a something squared with a plus or minus and a 1 or the other trig function, I always go to the Pythagorean identities, okay? But sometimes it's just like innate in us that like when we see parentheses, we want to distribute, which is fine. If you were to distribute here, I would have gotten sine squared x times 1, which is sine squared x, plus sine squared x times cotangent squared x. And then how can I rewrite cotangent squared x? Cosine over sine. And then what happens with my sine squareds? They cancel. I get sine squared x plus cosine squared x, which is what? 1. So 2 completely different ways to do it. Both would get 100% full credit. So even if you like do it a different way from somebody else, don't panic. Okay, they could both be right, which is why this quiz is going to be the most painful thing on the planet to grade, but it's what it is. If they could both be right, okay, you just got to make sure you're showing all those steps.
Wait, when is the quiz?
Friday. We're going to get lots of practice before then.
I tried by separating sine squared x to sine x and sine x over cosine x.
Then what?
And then I separated them like that. And then I turned sine over cosine to tangent. And then from the other side, I turned cosecant into 1 over cosine x. And then I divided both sides by tangent, which is right
Divide, well, let's just see. Divided both sides by tangent, like,
yeah. Like sine over.
so it's gone from here. And then this would be 1 over cosine x times tan, no, times 1 over tan. Because you'd have to do it times both, right? Minus cosine x times 1 over tan.
And I had turned the tangent into sine over cosine again.
Okay,
So I could cancel out the cosine.
so it would be cosine x over sine, right? Because this is the same thing as cotangent x, right?
Yeah.
Minus cosine x times cosine x over sine. So these you canceled?
Yeah. And then I was left
Minus, this would be cosine squared x over sine.
yeah. And then from there,
Did you combine that into one fraction?
yeah.
And then 1 minus cosine is the same thing as sine.
Because I
Is
just
there a less complicated?
I mean, as usual, Audrey overcomplicated it, let's be honest, but it worked. And it's right. Hey, listen, at the end of the day, it worked and it was right. That would get you all the points. Yeah. Any? Yeah.
I got confused, like, I don't understand what you just did, like, I get the beginning, but then towards the end I got lost.
So, like the dividing by tangent part, is that where I lost you?
That,
Yeah, so by dividing by tangent, you're multiplying by 1 over tangent, which is the same thing as multiplying by cotangent. So if you just took the 1 times 1 over cosine and the cosine and you multiply by cotangent, then you can change that to cosine over sine. And then from this one, the cosines canceled and you got 1 over sine. And then from the one on the right, they're not going to cancel, but they multiply together. So, but before you get too heavy into this one, like, let's try to see if there's another, because I'm not saying, obviously this is not wrong. This worked perfectly. This would get you all the points. But just because you don't see it that way doesn't mean that it's wrong. Anybody else try something different? Yeah.
I changed the sine squared x to 1 minus cosine squared x over cosine x. And then on the other side, I changed the secant x to 1 over cosine. And then I separated the 1 over cosine and 1 over cosine minus cosine x over cosine. And then I simplified the cosine squared x over cosine and got 1 over cosine x minus cosine x equals 1 over cosine x minus cosine x.
So even if you hadn't changed the right side, you could have changed this back to secant x minus cosine x. Remember, because if you remove cosine from the bottom to the top, it would have become secant. So yes, works. Left side equals right side, and all the steps in between are right. Where did what go? So he split this, which is something that is a great trick that not everybody sees. When you remember, we did this before the break. When you have a sum or difference in your numerator and a single term in the bottom, you can split it. Both terms in the numerator get that denominator, and sometimes that gets simplified. So like that 1 over cosine could have become secant, and then you could have just left it as secant x minus cosine x. It doesn't mean that it's wrong to change the right side as long as that left side equals the right side. Some people are peculiar, which is, I think, is dumb. Some people are peculiar about only changing one side, like they only let you change one side to get to the other side. Sometimes you reach a dead end and you have to keep working. So as long as the left equals right, I'm fine with it.
So it doesn't matter if they put 1 over cosine x minus cosine x, it like equals.
So you just have to make sure that literally the left side equals the right side.
Okay.
You would have had to change both, or you would have keep changing the left side to get back to the secant x minus cosine x, like that.
But as long as they equal each other.
Correct. Yep, because sometimes it's easier to work both sides.
Wait, so what would be the answer? Just
The work.
Oh.
Yeah. So the very last line should be the left side equals the right side, and it has to equal. So that's some people don't go all the way to the end sometimes. It has to equal. Left side has to equal the right side, but the work in between is what's going to get you the credit.
So could you leave it as 1 over cosine x minus?
Sure. Yeah, as long as that left side equals the right side, as long as you change both.
Miss Chris, why is it?
Yeah.
So it doesn't have to like equal like something that you started with?
Correct.
Oh, okay.
Sometimes you have to change both sides. Sometimes it doesn't work. Sometimes you get to a dead end and you have to change both sides. Doesn't mean you always have to, but sometimes you have to. All right, anybody want to give a go at number 2? What number is this? 6?
Can you show us how to square, like make them square?
Yes. So like if I wanted to, well, let me see if anybody has a try before I get to there. Anybody have a guess? Because I hate to take it away. As soon as I do it one way, everybody's like, oh, that's the way to do it. That's not necessarily true.
I have a guess, but I don't know how to do it with a square job.
So when you see a difference or a sum in the bottom of a fraction, even though that looks like it's one fraction, that's usually what you need to get rid of, because there's a sum or difference in the bottom, and that's usually more complicated. So the hard part here is we can't use the trick where we just move the secant and the tangent to the top, because that's a difference and not multiplication. If it's multiplication, you can move secant to the top, you can move tangent to the top, they can become their reciprocal functions. But this is a package deal, and you cannot break it apart. I can't just move part of that expression. So when you have whether it's a sum or a difference, doesn't matter what it is, in the bottom, and they're both part of a Pythagorean triple, which these are, secant and tangent are in that 1 plus tangent squared equals secant squared, then I can actually do it by, it's like rationalizing your denominator with an expression. So if I wanted to get them both squared, I can literally multiply by the opposite of this expression. So think about when we did square roots, like if we had 1 over 2 plus square root 3. Now this goes back a ways. But how did we get rid of that bottom? 2 minus root 3, right? Then we did it again when we had the i's, we did the conjugates, right? And that always got rid of that part in my denominator. So it's the same concept, except you're doing it with words instead of numbers. Yeah.
Why can't we like split the other one, but you can't split it?
Good question, because the other one had the sum in the top. So Vanessa just asked, how come we could split this fraction? Where was it? It was in the last, right? Or did Hunter do it in this one? No, he did it here. How come we could split this one, but we can't split this one? That one, the sum and difference is in the numerator. That's when you can split it. Okay? Or if it was a product in the bottom, I could split it. But if there's a sum or difference in the bottom, I can't split it. So I'm actually going to take and I'm going to multiply this by the opposite of this expression. So because that says secant x minus tangent, I'm going to multiply it by secant x plus tangent. Top and bottom, because that's the only way I could do it. So in my numerator, I get 1 times that, so it's secant x plus tangent x. In the denominator, that's the difference to 2, or this is going to be the result of difference 2 squares, right? Because they're the same expression, but one's a plus and one's a minus. So if you don't catch it and you FOIL it out, you'd get secant times secant, or secant squared x. Secant times a negative tangent, so minus secant x tangent x. Tangent times secant positive this time, tan x secant x. And negative and a positive and a negative, negative tan squared x. And then what happens is those middle terms cancel out because one's positive and one's negative. So again, this is what results in the difference of 2 squares, which would be secant squared x minus tan squared x. So that would be the denominator. Good. So secant squared x, go back up to my Pythagorean identities, right? If tan's on the side with secant and it's being subtracted from it, that whole thing can get replaced with a 1. And now I get secant x plus tangent x over 1, which is just secant x plus tan x. So sometimes you need to look for that trick. Sometimes you want your denominator to go away. And it's not like all the time, but it's part of your part of your Pythagorean identities. And so when you can do that by multiplying by the opposite of that expression.
Number 7.
Yep.
There's, it says 2 times secant squared x. I don't know.
So that one, the right side is more complicated. Try messing with the right side. When you have 2, and again, this is a great thing, so you're going to start to learn little tricks along the way. When I have 2 fractions with different denominators on one side, you're trying to combine them into 1. So what would be the least common denominator of 1 minus sine x and 1 plus sine x?
Is this like what we did a couple lessons ago when you would multiply by the other denominator than the numerator?
Yep. So I need my least common, I don't know if you heard her, but we multiplied each fraction by the opposite denominator because we have to get them to be one denominator. So my one least common denominator would be 1 minus sine of x and 1 plus sine of x because they are different. You cannot break those apart. So this 1, I'm going to multiply by 1 plus sine of x, and this one I'm going to multiply by 1 minus sine of x. So 1 times 1 plus sine of x is 1 plus sine of x, plus, because this middle is a sign, is positive. And then the right side, 1 times 1 minus sine of x would be 1 minus sine of x. Good. Now what? What'd you do?
So then I put it as like the sine x and negative sine x cancel.
Good.
So it's 2 over, and then I did 1 minus sine x.
because that's a difference of 2 squares, right? So that's like the one step you don't really have to show all that work for, because if you know how to do the difference of 2 squares, you can use the shortcut. So it's square the first one, square the second one, put a minus between them. And then what?
1 minus sine squared x is cosine squared x.
Good. 1 minus sine squared x is cosine squared x. That's one of your Pythagorean identities.
And then I split it into 2 over 1 times 1 over cosine squared x.
2. Okay.
And then I flipped it so it's secant squared x.
There you go. So I would just say you don't, I mean, it's fine, again, it's fine that you had it. You don't need this step, because remember, you can bring a function to the numerator by making it its reciprocal. So that's how I would show that step if you wanted to. You could just literally draw your arrow. Like, I'm bringing this to the top, and as I bring it to the top, it becomes its reciprocal function. Questions on that one? Sure. That's not the one I erased, right? No, okay, good. All right, number 9 says tan squared x plus 1 times cosine squared x minus 1 equals negative tan squared x. What do I do? Tan squared x plus 1 is secant squared x. That's one of your Pythagorean identities. Then what?
Cosine squared x minus 1 equals.
So why is it like that? Think about it. It's sine squared x plus cosine squared x equals 1, right? So how would I get it so that it's cosine squared x minus 1? I'd have to subtract the 1 from both sides and subtract the sine squared from both sides. So I'd end up with cosine squared x minus 1 equals a negative sine squared x. So pay attention to your signs there, because that could make a big difference, okay? If it was 1 minus cosine squared, then it's just a positive sine squared. But because it's cosine minus 1, you have to move the 1 with the cosine, which means you have to move the sign to the other side.
For the even odd identities, those ones can't be squared, right?
They can be, but the even and odd would have the negative on the actual angle itself. So it would say tan squared of negative x, and then you would know to make that negative tan squared of x. All right, now what?
Wait, so negative tan squared x is the same thing as.
So if it said tan squared negative x, that's the same thing as negative tan squared of x. Tangent, cotangent, sine, and cosecant are like that. Cosine, you just lose the sign. It goes right back to positive. Cosine and secant.
Can we turn tangent into sine over cosine?
You can.
And secant into 1 over cosine squared?
So try doing one more step here before you go back to that other one. So if I combine that into 1, it's negative sine squared x over cosine squared x, right?
Oh, it's the same.
And that's the same as negative tan squared x. I think. What could you do? Okay, so tangent, you have 2 choices, right? 1 over cotangent or sine over cosine.
Sine over cosine.
What's cosecant?
1 over sine.
1 over sine.
It's not.
Oh, that would be helpful. So So where can I go from here?
Cancel.
Cancel the signs.
And then 1 over cosine equals secant.
Good. So my request for you is that you make an attempt at every single question. So the homework for tonight's a PDF. That web assignment was so weird that you had to like plug it in random places. So it's just a PDF. It's just like this where you get the left side and the right side. My rule is nothing comes back in blank. There is always something you could at least start with. Even if you get to a dead end and you need to give up, we'll go over them tomorrow. But you have to start practicing these, okay? And then you can get to something like number 11. That's, in my opinion, super easy. So you never know when that's going to come. It could be at the beginning, it could be at the end. If number 1 stumps you on the homework, skip it. Try to do something, but then skip it and go to 2 until you find something that maybe builds your confidence level a little bit. All right, and then we'll finish the rest of these examples tomorrow. I'll answer questions on the PDF that's posted tomorrow. Can you know what it is?